All right, so the first section is asking us to simplify the log expressions completely. So that means we have to sort of figure out what the logs equal so that we can simplify them. So number one, remember that this is the common log, so it has a base of 10. So it is asking us 10 to what power equals 10,000? So 10, we can look at the zeros. When we have 1, 2, 3, 4 zeros, that means 10 to the fourth equals 10,000. So the answer, the simplest form of this log, when we simplify it, the answer to a log is always the exponent. So the exponent that makes this true is 4. Okay, number 2, 2 to what power equals 8? We know that x equals 3, so this log simplifies to 3. Okay, the natural log of e to the 7th, if we rewrite this in exponential form, remember that the natural log is a log with a base of e. So what this really means is natural log base e of e to the 7th. When the base and the argument are the same, it becomes 1, and we can bring this 7 to the front because that's what we do with exponents when we have them in logs. So we have 7 times 1, which means it just simplifies to 7. All right, Okay, letter D. Any log that has an argument of 0 always simplifies to, oh my goodness gracious, it's not writing. Simplifies to does not exist. So with logs, the two things we can't have are negative arguments and 0 arguments. So if you see an argument that is negative, we say it doesn't exist. If we see an argument that is 0, it doesn't exist. Anytime that we have a log, number E, letter E, that has an argument of 1, it always simplifies to 0, because what this is saying is any base to the 0 power will always equal 1. Letter F, log base 5 of 125. If I bring this 25 up, actually let's rewrite it like this. This is technically log base 5. If I rewrite 125 with a base of 5, 5 to the third, then I can bring it up above the fraction bar and make the exponent negative. I get log base 5 of 5 to the negative third. I can bring this to the front, which gives me negative 3 log base 5 of 5. And then this, when I have my base and argument the same, equals 1. So negative 3 times 1 is just negative 3. Letter G, I'm going to condense these logs. So remember, when I'm condensing, I multiply the arguments. So this becomes 8 log 25 times 4. So 8 log 100. Remember, there's an imaginary base 10 here. So 10 to what power equals 100? Well, 10 to the second equals 100, so that log goes away because 10 to the second power equals 100. So we multiply 8 times 2, which equals 16. And last one. Log base 5 of 50 minus log base 5 of 2. The bases are the same, meaning we can condense this log using division. So we go log base 5. We divide the arguments. And then this becomes log base 5. Oops, getting ahead of myself. Base 5 of 25. And then we ask ourselves, 5 to what power equals 25? And 5 squared equals 25. So the simplified version is 2. Number 2, expand and simplify. So we are expanding. So we're moving from one log to multiple logs. So we will expand the log. So this becomes, I'm going to split this up, natural log of 10. This was multiplication, so we're going to expand it to be addition, natural log of x to the 7th. Last thing we do is bring this 7 to the front. So our expanded version is natural log of 10 plus 7, just natural log of 10, not plus 10. Plus natural log of 7 or 7 natural log x. So that's our expanded version. Letter B, I'm going to start by separating these two, log of x squared, because it was division. We will expand using subtraction. So log x squared, log y to the 5th, and then I bring my exponents to the front. So I get 2 log x minus 5 log y. Letter C. Okay, I'm going to start by expanding. So I'll change this to log 3 of 27. This was multiplication, so I'm going to add as I expand log 3 of x squared. I can simplify log 3 of 27 to the number because 3 to the 3rd power is 27. This becomes 3. And then on my other term, I'm going to bring my exponent to the front, plus 2 log base 3 of x. And this is my fully expanded log. Okay, condense these logarithms. So now we're going to go the other way. So first, we'll take any coefficients that we have and move them to an exponential position. So natural log of x to the 7th plus natural log of y to the 4th. And then because we have addition, we can compress these or condense these logs using multiplication. So we'll do the natural log of x squared times y to the 4th. Because they're right next to each other, it is implied multiplication. You don't have to put a times sign. Letter B, we got the same base, so we can condense these logs using division. So this becomes log base 4, and our argument will be x over 12. Okay. Number 3. Okay, first step here, we're going to move our exponent or our coefficients to exponents. So we have log base 3 of x to the 3rd plus, log base 7 y to the 4th. Now, notice that the bases are not the same, meaning we cannot condense any further. This is our final answer because we can't now do multiplication because we don't have the same bases. So we just leave them separate. Last, we'll move our coefficient to a exponent. So we get log base 6 of x to the 1/4. And then I'm going to rewrite this because I know how to deal with fractional exponents. This becomes log base 6 of the 4th root of x. And that is fully compressed. Okay, graphing. We are going to draw the asymptote and label 2 points. So to start, we find the asymptote. We're going to set that equal to 0, our argument, x plus 2 equals 0. So x equals -2, that is going to be our asymptote here. Okay, then we'll do our anchor point. Remember the anchor point for logs is always at 1, 0. But then we're going to have a transformation. It's going to go left 2 and then down 1. So from my anchor point, I'm going to go left 2, down 1. So this is my new point after I've transformed my anchor. Then I'm going to choose one more point for x that makes sense. I have a log base 10 here. So I'm going to want to have something. Is that log base 10 or did I erase it? Oh, it is a log base 10. Okay. So I have a log base 10, so I want to choose something that's easy to work with, that 10 goes into easily. So let's do like, I think we could do 10. So yeah, if we choose a value for our argument that's going to easily work with a base of 10, we want to get something in that argument that equals 10. So if we plug in an 8 for x, then we get log base 10, essentially, but just log of 8 plus 2 minus 1. So then I get log of 10 minus 1. Remember that log with no base written is log base 10. So log base 10 of 10 simplifies to 1 minus 1, which is 0. So when x is 8, y is 0. That's the next point I can plot, which is out here. Okay, and then I just connect my points, I follow my asymptote, and make the shape of my graph and put my arrows on. All right, for number 5, I'm going to start with my asymptote. So I set my argument equal to 0. So x minus 1 equals 0. I will have a vertical asymptote when x equals 1. So I'm going to start with that. And then I'm going to plot my anchor point, which usually starts at 1, 0. And then it's going to go right, 1, up, 3. Right, 1, up, 3. Okay, so let me erase that original anchor point. So that's our new anchor. And then we choose one more point that makes sense. Again, we have that base of 10, so let's put something in for x that's going to make our argument equal 10. So if we choose x equals 11, plug that in. Negative log of 11 minus 1 plus 3. We get negative log 10 plus 3, and we remember that this is an imaginary implied base of 10. So log base 10 of 10 is 1, so negative 1 plus 3 is 2. So when x is 11, y is 2. This kind of goes off our graph, but we can kind of sketch it and label it because we'll know what it is. So if we go out to 11 and then up 2, this is 11, 2. This point is 2, 3. And then I follow my asymptote because of this reflection. It's going to fall from left to right. So negative log reflects vertically. And we can see that if we calculate our points correctly. All right, solving the log. Remember, if we have a log on one side and we have it isolated, the first thing we're going to do is rewrite this in exponential form. 21 to the second power equals 2x. And then 21 squared is 441. Then divide both sides by 2. So x equals 220.5. Number 7. Okay, same thing. We write in exponential form. 4 to the third equals 20x. 4 to the third is 64. Divide both sides by 20. And this is about 3.2. X equal, oof, gosh, that's a lot of equal signs. Number 8. 5 plus log base 2 of x. First step is we need the log all by itself. So we're going to subtract 5 from both sides. We get log base 2 of x equals 1. Now we've got one log. Rewrite in exponential form. 2 to the first equals x, which is just x equals 2. Number 9, exponential form. 2 our exponent. Answer to a log is the exponent. 2 to the fourth equals our argument, 9x plus 2. 2 to the fourth is 16. And then subtract 2 from both sides. So we get 9x equals 14. And then divide both sides by 9. So x equals 14 over 9. And you can just leave that as an improper fraction because it does not simplify. Number 10, first thing that we can do here is we can condense our logs because we have addition and we have the same bases. So we would have log base 8 of 12 times 4/3 x minus 7 equals 3. I'm going to distribute this 12 to both terms. So I get log base 8. 12 times 4/3 is 16. And 12 times negative 7 is negative 84. 16x, I forgot that x, equals 3. Okay, now I've got my log. It's down to 1 log on the left, so I can rewrite it in exponential form. 8 to the third power equals my argument. 8 to the third is 512. Then add 84 on both sides. oops, plus 84. 596. And then last step, divide by 16 to get x by itself. And x equals about 37.25. Last one, natural log of 5x minus 3 equals 2. First step, we want to isolate the log, so we'll add 3 to both sides. And we get the natural log of 5x equals 5. Then remember, natural log has a base of e, so when we rewrite this in exponential form, we get e to the 5th equals our argument. And then the last step, to solve for x, divide both sides by 5. And you can just leave this as e to the 5th over 5 equals x. All right, calculator section. So step 1 is to graph this function on your calculator and plot some points, including the asymptote. So our asymptote here, let me zoom in a little bit, is going to be at positive 4. 1, 2, 3, 4. So here. Okay, and then we have our calculator, so we can use our calculator to draw some points. There's one at 5, 3, 1, 2, 3. And there's not really an even one for a while. There's one at 14, 4, which is like out here somewhere. So it's going to come up and continue. So we've got our asymptote, we've got a couple points, and we have the shape correct of our graph. The domain of this graph, since we have that vertical asymptote, it's going to start at the asymptote but not include the asymptote. So it is going to go from 4 to positive infinity. So no bracket, just a parentheses. The range is all real numbers. It comes up from negative infinity and it will continue to positive infinity. The y-intercept, because of where this asymptote is, this graph will never intercept this axis. It will never cross the axis because it can't ever cross the asymptote. So for this graph, there is no y-intercept. The x-intercept, to find that on our calculator, we do second calc 0. And then it's not going to show up on your calculator, but it may calculate it still because it keeps going. So we do second calc 0, do our left bound and make sure that like your x value is left of the axis, so less than 0. And then go to the right so that it hits back up on your graph. Enter, enter, and it will calculate that 0. So the x-intercept is at 4.001. Okay, interval of increase or decrease. First of all, I need to identify if this is increasing or decreasing. If I trace my pencil along this graph, it is increasing from left to right. My pencil is rising from left to right. So I would circle that this is an interval of increase. And the interval is always the same as the domain. So it is increasing along its entire domain from 4 to infinity. Vertical asymptote we found was at x equals 4. Okay, end behavior to the left. We're going to say as x approaches negative infinity, so going to the left, we're looking at the left arrow. Our function is approaching the asymptote, right? So as our function, well, no, our arrow to our function is approaching negative infinity. So we're going to say negative infinity. And then to the right, as x approaches positive infinity, our arrow, the arrow of our function is going slightly greater forever. So it is approaching positive infinity. All right, f of 8.5, we're going to put in a second calc value and say when x equals 8.5, what is y? And that is 3.65 approximately. Then it says if f of x equals 3.5, find x. So we put in a y2 equals 3.5 and then do a second calc intersect. Which is at about when x is 7.16. Okay, Okay, couple of word problems. So this is a regression, so you need to put your values into your calculator, go into your stat, and then into your edit. And you're gonna put L1 for those and L2 for those. Okay, then once we have all that in, we calculate our linear regression. We're going to go into our stat calc menu, go down to the LN reg. So it says create a logarithmic model. That's how we know we're gonna use the linear regression. Okay, then A and B to the nearest hundredths place. So we're gonna go out 2 places. So our value, our equation is y equals negative 26 to the hundredths would be 0.48 plus, that was our A. Our B is 13.23 times the natural log of x. That is our equation. How well does the regression model the data? We look at our r-squared value, which equals 0.99. That means it is a good model because it is close to 1. Right? 0.99 is very close to 1. It says, what is the stopping distance of a car traveling 65 kilometers per hour? So that means when x equals 65, what is our y? So we can go to our y equals, we can type in this, or we could have stored it in our regression. So either way, your values might be slightly different based on what you do, but it'll just be by like probably 1 or less. So if we go to second calc value, in our graph, and we put in when x equals 65, make sure your window is big enough. Make sure you do a stat, a zoom stat, or increase your window so you can see all the way out, and then do a second calc value, put in a 65 for x, and when we push enter, we see that y equals 28.76, and this would be stopping distance in meters. So labeling, it would take it about 28 meters to stop if it was going 65 kilometers per hour. Then it says, what is the stopping distance of a car traveling 5 kilometers per hour? This is a y value. So we're gonna go into our y menu, put in a y2 equals 5, and then do a second calc intersect to find the value of x when y is 5. And that is at approximately 10.79 meters. Is it meters? Yeah, meters. Hold on, I did that totally wrong. Hold on. This is not a y value. This is just another x value because kilometers per hour is still an x. So we're just gonna do an x equals 5. So it's just another second calc value when x equals 5. And that makes 0 sense because here's the answer we get, that when x equals 5, it says that the stopping distance is negative 5.18. Can you go a negative distance when you are moving forward and put your brakes on? No. So this doesn't make sense. So you would say no because it's less than 0. So sort of just interpreting that data and recognizing like that doesn't make sense. You have to go some distance to stop when you're moving rather than going backwards. All right. We're going to solve for x. This is a calculator portion, so you can actually use the log buttons on your calculator and get exact values. So we are going to rewrite this in log form in order to solve for an exponent that is a variable. So we'll say log base 5 of 24 equals our argument. And then we want to get x by itself because that's what we're solving for. So we're going to subtract 5 from both sides, which is log base 5 of 24 minus 5 equals x. And you will put this into your calculator, go to your math menu, go to log base, and then you can put in a base of 5, argument of 24, go outside your parentheses, subtract 5, hit enter. The answer, our x value, equals negative 3.025. Number 3, e to the x equals 81. We're going to rewrite this in log form. Log base e is the same thing as the natural log of 81 equals the exponent. So then natural log is the button right below log. Natural log of 81 simplifies to 4.394. So we're going out 3 decimal places. Number 5, log base 10. So this is just the common log of 125 equals our argument, 5x plus 7. Now we got to get x by itself, so we'll subtract 7 from both sides, which is log 125. This is by itself, so we're going to sort of call this parentheses so we don't get it confused, minus 7. And then our last step is going to be, because we have equals 5x, so we have to divide both sides by 5. Be careful when you're doing your calculator work on this. You must follow order of operations. So when we put this into our calculator, we'll do log base 10, or the common log of 125. Then we'll subtract 7. Then we'll divide everything by 5. So log 125 minus 7 divided by 5 equals, x equals negative 0.981. And last one, number 6. 10e to the 4x minus 1. First step, we got to get this e isolated before we can start to rewrite it in a log form. So we get e to the 4x minus 1 equals 110 divided by 10 is 11. And now we can rewrite it in log form. Log base e is the natural log of 11 equals 4x minus 1. Then we'll add 1 to both sides. So we get the natural log of 11. We can't just add 1 to 11 because it's outside of our argument. Equals 4x, divide by 4, divide by 4. And then into our calculator, we're going to put the natural log of 11. Then we'll add 1, then we'll divide by 4 to get x. So natural log of 11 plus 1 divided by 4 equals, go out 3 places, 0.849.